This recording we're going to be looking at matrix rings, and the first thing is what I want to do is I want to let F be any field at all. Now the most common fields that people tend to work with, of course, are the real numbers, the rational numbers, the complex numbers. But it turns out that if we look at the integers mod a prime, that is a finite field. So we could be looking at any of these kinds of structures. And what I want to do is I want to define a set that I'm going to denote as M sub n of F. And this is going to simply denote the set of n by n matrices with the entries drawn from the field F. And the matrix addition and the matrix multiplication are going to follow our standard rules, except that the multiplication and addition inside those definitions will follow from the arithmetic inside of F. So basically what I want to be thinking of is that if A is an n by n matrix that has entries a sub ij, and B is a matrix that has entries b sub ij, where the aij's are all pulled from F and the bij's are all pulled from F, then what we basically have is that we can define the sum of the two matrices simply by adding their entries together, entry by entry, where the plus is done inside the field F, and then the standard matrix multiplication is done using the standard way that we do it for matrices back in an introductory course in linear algebra. The matrix product AIB, I'm going to say that let's call its entries Cij. And the thing is that Cij represents row I of the first matrix dotted with column J of the second matrix. And what this actually means is that Cij is going to be AI1 times B1J plus AI2 times B2J plus AI3 times B3J, and we keep going until we get to AIN times BNJ. And in this particular thing, all of this arithmetic is done inside of our field F. So if we're in a finite field, the multiplication and the addition are being done inside that finite field. If we're in the real numbers, this is just exactly what we would normally think. If we're in the rationals or the complexes, it works just like the reals do. Well, it turns out that the set of n by n matrices whose entries are drawn from F under matrix addition and matrix multiplication is always going to be a non-commutative ring with a multiplicative identity element. And what we want to do in this particular video is prove this fact. So, to show that the set of n by n matrices with entries drawn from a field F under its normally defined addition and multiplication is a ring with a multiplicative identity, we essentially have to show that all of the ring axioms work. And what I want to do is I want you to think back to your introductory course in linear algebra. And so we're really just going to do a sketch of this proof. And the reason why is that the calculational details, so the computational details, are exactly the same as showing that matrix addition and matrix multiplication have the properties that they do back in a linear algebra class where you're focusing in on M in N, which would be the set of N by N matrices where their coefficients come from the real numbers. So we're not going to go through all of the computational details because they really are the same as those linear algebra ones. But this is what I kind of want to say about this particular ring. So the first thing is that matrix addition and matrix multiplication are closed inside our set. And this basically just comes directly from the definitions. So from the definitions. The second thing is that plus and times are associative inside of our set. Now, the thing that I want to say here is that plus is associative is easy. We can write that down right away. If I look at letting A be the matrix whose entries are Aij, B be the matrix where the entries are Bij's, and C is the matrix where the entries are Cij's. A plus B plus C winds up being Aij plus Bij plus the matrix of Cij's, and that will be, let's actually give myself a little bit more room. That'll be Aij plus Bij with parentheses, and then plus a Cij, like that. But these entries are all in F, so this addition is in the field F, and so it is known to be associative, so we can stick those parentheses in this particular position instead. And when we do that, we wind up getting the matrix of Aij's plus, in parentheses, the matrix of Bij's plus the matrix of Cij's. And that turns out, of course, to be A plus B plus C. So addition is associative. Showing that times is associative is a lot messier. And instead of doing that, I'm simply going to say, look this up in a standard linear algebra text. But it does turn out that A times B times C will be A times B times C. Okay, so we have closure. Well, let's see. And we have associativity. The next property that we need to have, of course, is that this would be our third ring axiom. Plus is commutative. Well, that's easy. So this one is an easy one. If I look at that matrix and I add him to this matrix, well, that's just adding the Aij's to the Bij's. But this addition here is inside F, and multiplication commutes inside F because F is a field. So we can swap the order of those two guys, and then we get that the matrix of Aij's plus Bij's is equal to the matrix of Bij's plus Aij's. So commutativity is not a problem. The next axiom is the distributive laws, and it is laws, so the distributive laws. In any kind of a matrix ring. And here again, this is one that I'm going to say the computational details are just like they are back in your sophomore class in linear algebra. So they are the same as the standard proof in a basic course in linear algebra for the matrix ring capital M sub n, where all of the entries are the real numbers. But the distributive laws say that A times B plus C winds up being AB plus AC. But we also have B plus C times A on the back end is going to be BA plus CA. Because matrix multiplication is not commutative, in a standard matrix ring, multiplication is not commutative. These two laws, these two distributive laws, say functionally different things. They say that you can only factor a matrix out if it's on the same side of both of the terms. So in particular, we do not have AB plus CA equals, say, A times B plus C, and we do not have AB plus CA is equal to B plus C times A. So neither one of those things works in a matrix ring, just like they don't work back in your standard sophomore course in linear algebra. So let's just kind of remember what we've done. We've shown plus and times are closed. We've shown plus and times are associative. We've shown plus is commutative, and we've shown that we have distribution laws. So in order to get a full-fledged ring, the last two things that we have to show are the existence of an additive identity element and the existence of additive inverses. So the fifth ring axiom, this structure, the n by n matrices with their entries drawn from F, has an additive identity element. It's no surprise that the additive identity is simply going to be the matrix that is made up of only zeros. So in other words, in a set of 3 by 3 matrices, the zero matrix would look like the 0 in the field 3 times on the first row, the 0 in the field 3 times on the second row, the 0 on the field 3 times on the third row. In a typed set book, it's traditional that this name is usually a boldface zeros, whereas these zeros inside the individual field are not bold-faced. There's no easy way of indicating that inside handwriting unless you want to do something like put a bar over this 0. So we'll do that. It's easy to, this one is an easy one to verify. If we've got A plus the zero matrix, we're looking at a matrix of aij's plus a matrix of zeros from the field, and our standard definition says that. But because the zero is the additive identity in the field, this just becomes the matrix of aij's. And similarly, if you put the zero matrix on this side, you basically are looking at 0 plus aij, and that is again just going to be the matrix of aij's. So we easily have an additive identity, and it's no surprise that the additive inverse is exactly what we think it is based on our knowledge from a sophomore course in linear algebra. So additive inverses. If I take a matrix made up of aij's inside the set of n by n matrices with entries from F, then no surprise, minus A is just look at the additive inverse of every single entry. And it's easy to see that A plus minus A is the matrix full of aij's plus the matrix full of minus aij's, and that will be aij minus aij, and that's the matrix that is full of the zeros in the field, which is just the additive identity for our structure. And I want to kind of tie this video up with just a few observations. So the first observation is the calculations needed to show that the set of n by n matrices with entries drawn from a field, they actually look the same regardless of the choice of the field. In other words, the symbolic computations that you use are absolutely identical, which is why I did not go through those difficult parts of the proof from linear algebra. The second observation is that in all of these matrices rings, you can easily show through examples. So examples can be found where A times B is not equal to B times A. So these matrix rings, are always non-commutative. Now there's finally one more fact that I meant to show a little bit earlier, but we're going to do it right now as an observation. The third observation that I want to make about every single matrix ring is that since F is a field, we know that there is a multiplicative identity in F, and that means that we can create a matrix that has that multiplicative identity on its main diagonal and zeros everywhere else. And this matrix is traditionally called the n by n identity matrix. And this guy is a multiplicative identity for our ring of matrices. And let's just look at that particular fact kind of quickly. So this matrix looks like 1, 1, all the way down to a 1, and zeros everywhere else. And these zeros, of course, also still belong to the fields. In other words, little ij, well, let me call it this way. If I write capital I is equal to, say, let's call it Cij, Cij is equal to the 0 if I is not equal to j, and Cii is equal to 1 if I is equal to j. And it doesn't matter what field we're in, so I'm going to slap subscripts on that additive identity and that multiplicative identity. Well, if you look at A times I, that is going to have row I of matrix A dotted with column J of the identity matrix, and the only entry in column J that will not be a 0 is the jth entry. So this is going to mean that that ith j entry is going to be Aij, and that's going to wind up being the matrix A. On the other hand, if I look at that product going the other way, the identity first and then the matrix A, this will be row I of the identity matrix dotted with column J of the A matrix. And again, the only entry in row I that is not equal to 0 is the ith entry, and so that dot product is just going to pick up Aij, and that again is the matrix A. So at this point we know that the set of n by n matrices where the entries are drawn from a field is always a non-commutative ring with a multiplicative identity element.